Okay, thanks very much for the invitation to speak at this very interesting workshop, obviously a topic very near and dear to my heart. And thanks to all of you for attending, albeit remotely. I'd like to talk about some of our recent sim2real work, actually on 3 different robot platforms: biological robots, soft robots, and compliant robots. I'm going to focus today specifically on our efforts to try and scale this up. Can we automate not just the design of robots in silico using an evolutionary algorithm, but also automate the deployment of evolved designs? There's 3 different ways we could do this. We could obviously fix the robot in reality, fix the robot in simulation, and then evolve policies and transfer them across the gap. Myself and others have worked on shape optimization, so optimizing the 3D shape of soft robots and then transferring some of those shapes across the gap to physical soft robots. But in particular, our focus is usually on topology optimization. So assuming that we're going to change the number of elements of which the robot is composed, we might be adding and removing physical structure, adding and removing sensors and motors, and so on. And as I'm going to show you in this talk, we can often reduce the gap between simulation and reality better by searching for particular shapes and topologies. So in essence, compared to transferring just policies for fixed robots. In other words, the body plan of the robot can, in some cases, facilitate sim-to-real transferal. In all 3 applications I'm going to show you today, we used multi-objective optimization, where we have a population of solutions represented by the points here. We visit each point and tag it as either dominated red or non-dominated green. A solution is dominated if there is some other solution in the population that is better at both objectives than the candidate solution. So you can see in this case, there's a number of dominated solutions, 4 non-dominated solutions. Typically, we delete the dominated solutions and make randomly modified copies of the non-dominated solutions, pushing, in this case, up and to the right, trying to maximize both objectives. In a lot of the work, we're trying to trade off fitness, which in this case is speed of displacement, against efficiency. You can see in this particular evolved soft robot here, it's not efficient. All of the voxels are increasing and decreasing in volume. Basically, every single element of the robot here is a muscle. This is basically a muscle in a particular shape. At the other extreme, you can get things that are very efficient but move slower, like this particular soft passive dynamic walker evolved by Francesco Carucci from Cecilia Lasci's group a few years back. Okay. So again, some of this may be familiar to some of you. We encode our robots using cppns developed by Ken Stanley. cppn is a generative network that takes as input a set of coordinates and then spits out either an amount of gray onto a 2D pixel, or when cppns are applied to soft robots, as was first done by Nick Cheney and Hod Lipson a few years back. We visit each coordinate of a lattice inside an empty cage. We take the X, Y, and Z coordinate of that point in the cage, propagate it through a cppn, which basically composes coordinate transforms, and the values that arrive at the output layer. In Nick's original paper, one output neuron dictates whether a voxel is deposited at that location or not, and the other output neuron dictated which of 4 material properties to paint onto a voxel if that voxel is deposited in that location. In this work, red and green voxels increased and decreased in volume and antiphase to one another. Light blue voxels were passive soft material. Dark blue voxels, of which there are none here, are passive stiff material like bone. In some recent work, we show that this form of topology optimization, where we're depositing fewer or more voxels from one cppn to the next, this evolutionary approach to topology optimization actually outperforms state-of-the-art stochastic gradient descent and also state-of-the-art stochastic gradient descent with restarts. In this case, we considered creating soft robots inside an empty 2 voxel by 2 voxel by 2 voxel cage. Given that small design space, we can enumerate all of the possible robots that can be built inside that volume. We know the entire search space. And it turns out that in a 2 by 2 by 2 design space, there are 5 optimal solutions, 5 global optima. Given 10,000 generations of a multi-objective optimization process, evolution was able to consistently find one or more of these optimal designs. Stochastic gradient descent did okay, but not quite as well. When we increase the design space to 3 by 2 by 2 voxels, there are a much larger number of robots, but it is still an enumerable space. We were able to evaluate every single robot in that design space and determined that, again, there were 5 optimal solutions. Evolution consistently found those 5 solutions. SGD and SGD with restarts did not do so well. And the gap in performance between evolution and stochastic gradient descent increased when we moved to 3 by 3 by 2, which was the last remaining design space that we could exhaustively enumerate and know when we had found the optimal solution. So a number of reasons why an evolutionary algorithm outperforms stochastic gradient descent in this space. One of them, which has already been shown with cppns, is cppns tend to bias the search space towards regular structures, like you see here, rather than just random constellations of voxels. In this case. The other reason is that stochastic gradient descent typically performs well for fixed length problem formulations where the parameters are real values. In the case of topology optimization, we have more or less integer parameters. So a 0 can indicate no voxel is present, 1 can indicate a passive voxel is present, and a value of 2 indicates that an active voxel is present. Doesn't mean that there aren't adaptations to stochastic gradient descent that could be made to apply gradient descent in this problem space. But basically an evolutionary algorithm is the way to go for the moment. So the first of 3 applications I wanted to show you is automated design and deployment of compliant systems. In this case, this is a collaboration with some colleagues at the Department of Defense and the Australian government, where we were looking at evolving the shape of flapping wings for small-scale ornithopters. In this case, as you can see at left, the evolutionary algorithm is designing the number and shape of panels for a wing. We simulate some first-order approximation of aerodynamics in Open Dynamics Engine, a pretty simple simulator. The construction of the wing itself is manual, but once attached to the test harness that you can see here, all analysis and testing of the physical wing's performance is automated. We're looking at ways to automate the construction and attachment of the wing to the harness next. The second application was applying sim2real to biological robots, otherwise known as the Xenobots. This was published at PNAS this past January. You can see an evolved design in simulation at the top and then transferred to reality. In this case, the design task is particularly challenging because, first of all, there is no control policy. The biological robots were eventually built from frog skin cells, which are the passive cyan voxels you see here, and frog heart muscle cells, which are the green and red voxels that you see here. Heart muscle cell and frog, if put together in the shape of an adult frog heart, will spontaneously synchronize and pump blood in and out of the heart. But if you rearrange heart muscle tissue in an unfamiliar pattern, there is no guarantee that those cells will synchronize. So in simulation, we added a constraint which assumes that wherever the cppn deposits heart muscle tissue, that tissue will beat at a random phase offset compared to other patches of heart muscle tissue. You can see that in the video by the random flashing of red and green, indicating that the heart muscle cells are increasing and decreasing in local volume at different phases from one another. So the task for the evolutionary process in this case is in essence to find a 3D shape and distribution of skin and heart muscle cell that collectively de-randomizes the action of the random motors in this case. So that's a particular challenge. This design does it somewhat. And we got a pretty good sim2real transferal. Details about how we transferred and proved successful sim2real you can find in the paper. And the third and final application I'm going to talk about this morning, we tried to perform a more or less one-to-one sim2real transferal from simulated voxel-based robots to physical voxel-based robots. The physical robots are constructed of hollow voxels using an elastomeric material, which I'll show you in a moment. The advance we reported in this paper was again to try and increase the scalability of sim2real by transferring over 100 designs, evolved designs from simulation to reality. I'll just let this video play. This shows you how we actually go about manufacturing these physical robots. It's a low-cost, low-skill manufacturing process. What you'll see in a moment is the deposition of dragon skin and an elastomeric material. That we then deposit inside an open face mold to create the 5 of 6 faces for each of the voxels. Putting this on this rotational molding machine allows us to automatically try and create a uniform deposition of the elastomeric material on the 5 edges. And then once the elastic material has cured, we manually cut out the voxels. As you'll see in a moment, we're going to apply tubing to allow us to supply air inside the voxels. So we're going to use a hole punch in a moment to, after connecting the voxels together, use a hole punch to connect the air chambers between neighboring voxels. And then to create the 6th and final face for each of the voxels, we deposit a little bit more dragon skin material and then deposit our voxels on top. This is a very low-cost process. The total amount of materials costs about $200 US. You get all of the materials from Amazon. As you can see here, it's a relatively simple process to manufacture. Here you can see the insertion of tubing, so we can apply pressurized air to increase the volume of the voxels and extract using a syringe air from the voxels to decrease their volume. In that paper, we researched and reported on all the sim2real transferal efforts reported in the literature. If we're missing your work in here, we apologize. We'd love to hear about it. Add it to the list. This is our attempt to try and create a benchmark for our field, which reports, again, all the sim2real transferal attempts and lists for each attempt the number of controllers that were transferred from simulation to reality, at least those that were reported in the paper. But importantly, the number of different morphologies that were designed in simulation and transferred to reality. And you can see that in the work that I just showed you, we designed and manufactured over 108 distinct morphologies. The flapping wing application that I just showed you recently, we transferred 16 different wing designs from simulation to reality. What you see here are 9 of those 108 designs, and we're reporting for each of those designs how well it transferred from simulation to reality. The pink curves represent the predicted displacement of those designs in simulation, and the blue-green curves show the actual displacement of these robots when performed in reality. As you'll notice, they have no sensors, and we're using the syringes as actuators to supply and remove air, so very simple open loop control. You'll notice that in this case, for several of the designs, there was good prediction in terms of the magnitude of displacement, but very poor prediction about the accuracy or the direction of travel. So this shows us that the actual physical design of the robot can greatly influence the gap between simulation and reality. And this points us toward future work where we'd like to try and design, we'd like to actually design the body plans of robots to facilitate the reduction of the sim2real gap. I'd like to conclude by thanking all of my collaborators and colleagues, my PhD student Sam Kriegman and Doug Blackist and Mike Levin at Tufts for our work on computer-designed organisms. You can find all the source code, paper, images, and videos for that work at cdorgs.github.io. I'd like to thank our Yale colleagues for the work on scalable sim2real soft robots. All of detailed instructions for buying the materials and constructing physical soft robots can be found at voxcraft.github.io. And finally, I'd like to thank our colleagues at DST Australia for their work on automating the sim2real of compliant flapping wings for small ornithopters. And finally, I'd like to thank the financial sponsors of this work, DARPA, NSF, the Vermont Advanced Computing Corps, and the Australian Department of Defense. Thank you very much.